We now discuss the NAND implementation, and we observe that NAND gate is known as a universal gate because any logic expression may be implemented by using NAND gates only. And one easy method of implementing logic functions with NAND gates is to reduce them to the SOP form. Remember, the SOP form was y is equals to AB plus ABC plus ABCD, etc. So if you can express any expression using any form, you can introduce double bars representing two NAND gate operation, and therefore you can be able to say that the first inversion is one NAND gate, and the second one is a NAND gate that is used as an inverter. It is very simple and very straightforward. Again, you can be able to implement an inverter using an AND gate by this is an AND gate with two inputs. If you short these two inputs and you say that this is the input A, you will get A bar here. No matter what, this is what the truth table of an AND gate says. Remember that we said that the NAND gate outputs are 1 when the two inputs are 0, and therefore if you put this to be 0, getting in there, the truth table says that the output will be a NAND. That is how we say you can be able to implement a NOT using a shorted inputs of the two input NAND gate. That gives you a NOT. So the SOP form requires that AND and OR gates whose operations can be realized with NAND gates. That means that we are going to be replacing AND and OR gates with the NAND gates. And the AND OR circuit is equivalent to a NAND circuit. The key idea here, again, I repeat, is to understand that you can be able to implement an inverter using a NAND gate. Once you are able to do that, you just need to know that you can introduce double bars, which the first bar performs a NAND operation and the next one performs a NOT operation, and therefore you are able to perform an AND OR operation using a NAND. So we look at an example in which case we are asking ourselves, how can we convert an AND OR circuit to become a NAND circuit? And this circuit is simply expressed as I would want to use bars. So this is A bar dot C D bar, and then these two are barred. So if you are given such an operation, you can use the Morgan's theorem to break it into saying break the line and change that sign. So you break this line, becomes plus. Break this line, becomes plus. Break this line, becomes plus. So what do we have at the end? We have, first of all, break the first one. We have A, B, bar dot or plus C, D, bar. Oh, and again, you remember, we may not need to do that. You can know that double bars cancel themselves, that we have A, B, or C, D. So we are saying this was a NAND circuit because it was involving NAND gates, but now this is an OR circuit, AND OR circuit involving only AND and OR. That is the one example. This means that the AND OR circuit can be implemented using NAND gates only by substituting the AND gates and the OR gates with the NAND gates. That is what we have seen, and we have said that if you are, this is our AND, we have developed, this is a apostrophe not a comma, which we have been able to implement using AND and OR, but we are also saying that this one is equivalent to simply A, B bar, C, D bar, and you bar the two of them, you get your A, B, C, D, and this is what we have seen that is equivalent to what we had earlier. So these two circuits are equivalent. So again, we have another example here that tells us to implement the given logic expression with NAND gates only. We observe that this is made up of an inverter, a NAND gate, and all gates. My best approach is very simple. Introduce double bars here, and then change the sign, break the line and change the sign, break this line and change the sign. That will end up with A bar, B, that bar comes there, dot B bar D bar dot C bar cancels out, and our outer bar comes right there. Therefore, this can be implemented using an inverter, which is an AND gate. This is an OR AND gate, which again are inverted becomes an AND. Similarly, all these can now be implemented using an inverter and an AND gate. So that this is what this equation represents. And finally, this becomes our AND NAND equivalent. I write our equation which we had here, which is y is equals to a b bar b bar d plus c bar. What we have done is to introduce double bars, but we apply the De Morgan's theorem. That second bar changes as follows, comes at that point, cancels that. The sign changes from plus to dot, and the other double bar remains at the top. So this becomes, you can see now our A is being inverted. This becomes a bar. This is what we are getting right here. B is without an inversion, so it goes to form this NAND gate between A bar and B. So this is our second NAND gate. That is what we get right there. And then similarly, we have B inverted gets inverted by this NAND gate. And similarly, C is not. So at the end, we have this final bar resulting to give us the final NAND inversion. So we note that for an expression in SOP form, the implementation requires a AND gates whose output serve as an input to all gates. Thus, from the input to output, a signal must go through a minimum of 2 gates. This is called two-level implementation. The invert gate can be implemented with an AND gate by shorting the inputs of the NAND gate to serve as single input. The rest of the add all configuration can be implemented in NAND gate by substituting the AND gates and OR gate with an AND gate. And I think I have demonstrated that to allow us to represent our equation to the form that we desired it to be in NAND equivalent circuit.